Hi class, in this video we are going to learn about the fourth quantum number known as spin quantum number m sub s. So far we have seen three quantum numbers that describe the spatial location of an electron. They are principal quantum number n, which tells me about the shell that the electron resides in and gives me an indication of the energy and distance that those electrons are from the nucleus. Angular momentum quantum number L tells me the subshell, S, P, D, or F, and indicates something about the shape of that region of space that can be occupied by electron density. And magnetic moment quantum number M sub L tells me something about the orientation of those orbitals in space, and the number of M sub L values tells me the number of orbitals of that type. Okay, and we were using an analogy of an address where N would be the city, L would be the street, and M sub L would be the house number. So we know exactly where this electron would reside in the atom. The existence of a fourth quantum number was discovered by the Stern-Gerlach experiment, which passed neutral silver atoms through a magnetic field. And once these silver atoms were passed through the magnetic field, it was observed that they split and were deflected into two beams. And the fact that this was observed allowed the scientists to conclude that atoms actually were behaving as small magnets. And the fact that we observed just two beams meant that those magnetic dipole moments could have two possible directions. And with only two values possible, we can say that the magnetic moment is quantized, right? Quantized meaning there are only certain allowed values that it can be. So we give these numbers plus 1/2 or minus 1/2. And this is what we assign to m sub s. So m sub s will actually be a number that goes with a specific electron. It does not tell me about a location. We use a simplified model of a spinning sphere, much like a spinning top, to illustrate the idea of electron spin. And they can have magnetic moment of spin up or spin down, corresponding to plus 1/2 or minus 1/2 values. It turns out that no two particles can have the same quantum state, meaning that they can't have the same four quantum numbers. And this is known as the Pauli exclusion principle, which was named after Wolfgang Pauli in 1925. And this implies that each orbital can hold no more than two electrons. Let's illustrate this by looking at the three electrons in a lithium atom. So if we start to place electrons in orbitals, we would start by placing them in the lowest energy. We represent electrons in these orbital diagrams with half arrows. One in the up direction indicating a spin of plus 1/2, and one in the down direction indicating a spin of minus 1/2. So if I think about the quantum numbers that are assigned to this 1s orbital and this electron that I've placed there, n, l, m sub l, and m sub s, the first electron that I placed there would be in n equals 1, it's an s orbital, so l equals 0, m sub l would equal 0, and m sub s for the spin up would be plus 1/2. If I place a second electron, it can't have the same four quantum numbers, so it would have to be spin down. M sub s becomes the differentiating number for us in this example. Then if we're adding a third electron to make this lithium, we would add it in the next orbital, because there's no additional possibility for an m sub s. So having only two possible m sub s values means that only two electrons can be in each orbital. The third electron would then have a different set of quantum numbers, 2, 0, 0, plus 1/2. So you can see that this will have implications as we are exploring the true structure of an atom and filling electrons into orbitals. So thank you for watching. Let me know if you have any questions, and I'll see you next time.